Hello, welcome back. Now, in today's lecture, we shall introduce a new function associated with integer valued discrete random variable. Now, you suppose that x is an integer valued random variable with a probability mass function pk, that is equal to probability that x assumes value k, where k takes values 0, 1, 2, 3, etc. This is an integer valued random variable with the PMF is pk. And we define a function called p of x, capital P of x, which is equal to summation over k equal to 0 to infinity pk s to the power of k, which converges for modulus s less than or equal to 1. That is, in the interval minus 1 to plus 1, this function converges. Okay, and this is of course a power series, a converging power series, and called the probability generating function. And you remember this function gives you the probabilities. As if you know this function, then you can take the coefficient of s to the power of k, and that coefficient is pk. So once you have probability generating function PGF, you can find the probabilities as the coefficient of s to the power of k. And this function will be useful in stochastic process, mainly in Galton-Watson branching process, which you will study in your third semester. And many results associated with the PGF will be useful for that purpose. Okay, now we will see, later we will see that how the probabilities can be determined using PGF. Before that, we consider some examples. You consider first the Poisson random variable capital X, which is an integer valued random variable whose probability mass function is pk e to the power of minus lambda, lambda to the power of k by k factorial. K takes values 0, 1, 2, 3, etc. And you can find the PGF, which is P of s equal to summation over k equal to 0 to infinity pk s to the power of k. And you can see that this is on simplification, you will see that this is e to the power of minus lambda into 1 plus lambda s plus lambda s square by 2 factorial plus etc., which is equal to e to the power of minus lambda into e to the power of lambda s, because this function 1 plus lambda s plus lambda s whole square by 2 factorial plus etc. is simply e to the power of lambda s, and on simplification you will get this is equal to e to the power of minus lambda into 1 minus s. Okay, and you can find the PGF of many examples. Before attempting some more examples, we come to some important remarks of this function P of s. First, you can see that the PGF evaluated at s is equal to 1 is equal to 1. And the proof is very simple. You take P of 1, which is equal to pk s to the power of k. I have made a mistake here. Here this is not 1 to the power of s, but it is 1 to the power of k. Okay, and it is equal to k equal to 0 to infinity summation pk equal to 1. Okay, so the probability generative function evaluated at s is equal to 0 is 1, and you can take this as a property of probability generating function. It is a very fundamental property of probability generating function PGF. And in the second remark, you will see a technique of finding the mean and variance of an integer valued random variable using PGF. you can see that the first derivative p prime s, that is d by ds of p of s, that is equal to d by ds of sigma k equal to 0 to infinity pk s to the power of k. On differentiation, you will see that it is summation k is equal to 1 to infinity pk k into s to the power of k minus 1. Okay, and you evaluate this at s is equal to 1, you will get d by ds of p of s at s is equal to 1, which is p prime 1, that is equal to summation k is equal to 1 to infinity k into pk, or summation k is equal to 0 to infinity k into pk, which is equal to expectation of x. So expectation of x, by definition, this expectation x is the mean of the random variable, which is nothing but p prime 1. Okay, p prime 1. And similarly, you can find the variance also, and for that purpose we find the second derivative and evaluate at s is equal to 1. So p double prime s, that is d2 by ds2 p of s, that is second derivative. This second derivative കാണുമ്പോൾ അത് that is equal to summation k is equal to 2 to infinity pk into k into k minus 1 into s to the power of k minus 2. അതായത് ഫസ്റ്റ് ഡെറിവേറ്റീവിനെ വീണ്ടും ഡിഫറൻഷ്യേറ്റ് ചെയ്യാം. Okay, and when you evaluate at s is equal to 1, you get p double prime 1, that is d2 by ds2 p of s at s equal to 1. It is equal to sigma k equal to 2 to infinity k into k minus 1 into pk, or simply k is equal to 0 to infinity k into k minus 1 into pk. Both have no difference, and by definition it is equal to expectation of x into x minus 1. Okay, and of course you can generalize this. You can take the third derivative, fourth derivative, etc., the rth derivative, and evaluate at s is equal to 1. That is dr by dsr, that is you are finding the rth order derivative of p of s, and you evaluate at s is equal to 1. You can have simple generalization, which is equal to expectation of x into x minus 1 into x minus 2 into etc., x minus r minus 1, that is x minus r plus 1. Okay, so you can have this is the right hand side is nothing but the rth order factorial moment. You can see, you can define the rth order factorial moment of x as expectation of x into x minus 1 into x minus 2 into etc. Okay, and you will see how variance can be obtained. You know the definition of variance. Variance of x is expectation of x square minus expectation of x the whole square. It is a very common definition of variance, and that can be written as x square can be written as x into x minus 1 plus x. On simplification, you will get the quantity inside the square bracket is equal to x square and minus expectation of x the whole square. And again you simplify this, expectation of x into x minus 1 plus expectation of x minus expectation of x the whole square, and this is the second derivative evaluated at s is equal to 1, and this is the first derivative evaluated at s equal to 1, and the square of it, that is p double prime 1 plus p prime 1 minus p prime 1 the whole square. It is the variance. So a simple technique you can have for finding the expectation of x and variance of x, and I have consolidated these two results here in this box. Expectation of x equal to p prime 1 and variance of x equal to p double prime 1 plus p prime 1 minus p prime 1 the whole square. And of course this will be very useful for your branching process in stochastic processes. Okay, now we will have some examples before going for more properties of the probability generating function. We can have some examples how to find expectation of x and variance of x using PGF. Here we consider the PGF which we have just evaluated earlier, which is the probability generating function of Poisson distribution, which is p of s equal to e to the power of minus lambda into 1 minus s. You take the expectation which is p prime 1, That is, you find the first derivative and evaluate it at is equal to 0. That is d by ds of e to the power of minus lambda into 1 minus s at s is equal to 1. And you can see that this is e to the power of minus lambda into 1 minus s into lambda at s equal to 1, which is equal to lambda. That is a mean of the Poisson distribution is equal to lambda. And similarly, you will see that variance is also equal to lambda. For that purpose, you find the p double prime 1, which is the second derivative of the PMF, or d by ds of the first derivative at s equal to 1. And this is easily obtained as lambda into e to the power of minus lambda into 1 minus s into lambda, that is lambda square into e to the power of minus lambda into 1 minus s. By putting s is equal to 1, you will see that it is clearly lambda square. So you use the formula for variance, which is p double prime 1 plus p prime 1 minus p prime 1 the whole square. On substituting this, you will see that it is equal to lambda. And this substantiates the result for Poisson distribution. You know that for Poisson distribution, mean and variance are equal. Both are same and is equal to the parameter of the Poisson random variable, which is lambda. Okay. And similarly, you can consider some more example. Here we consider the geometric distribution with the probability mass function pk equal to q to the power of k into p, which is equal to k 0, 1, 2, 3, etc. And this is one way of defining the geometric random variables PMF. And some variations are also there for defining geometric distribution, but this is one way of defining geometric distribution. You know that geometric distribution can be modeled for coin tossing experiment until a head occur, and you are counting the number of tails before the first head, and you will find that the probability mass function is pk, that is equal to q to the power of k into p, k equal to 0, 1, 2, 3, etc. And what is the PGF? It is equal to summation k is equal to 0 to infinity pk s to the power of k, where pk equal to q to the power of k into p. So you can write this is equal to p into sigma k equal to 0 to infinity q of s to the power of k. And you know that this is a converging series which is whose values is 1 minus q of s to the power of minus 1. So this becomes p into 1 plus qs whole square plus etc. And finally you will see that the probability mass function is equal to p into 1 minus q of s to the power of minus 1. Okay. And now you will see how the mean and variance of this geometric distribution can be find out using the using the PGF, probability generating function. Okay, you can have this first derivative evaluated at s equal to 0, s equal to 1, then that is d by ds of p into 1 minus qs to the power of minus 1, which we have determined so far, and you evaluated s equal to 0 after finding the derivative after differentiation. So that is equal to p constant can be taken out, then minus 1 into 1 minus qs to the power of minus 2 into minus q. On simplification, you will see that it is equal to q by p. Very direct, you can easily verify this thing. And you find out the second derivative of p evaluated at s equal to 1, that is p double prime 1. It is equal to the derivative of the first derivative, that is second derivative. So it is equal to pq into minus 2 into 1 minus qs to the power of minus 3 into minus q. And direct simplification will yield 2 into q square divided by p square. Okay, that is p double prime 1. So you use the formula for variance. Variance is equal to p double prime 1 plus p prime 1 minus p prime 1 the whole square. And on simplification, you will see that it is equal to q divided by p square, because q plus p is equal to 1 for geometric distribution, because p is the probability of success and q is the probability of failure for a Bernoulli trial. So variance is equal to q divided by p square, and mean is equal to q by p. Okay, this results also substantiate the earlier result you might have studied in geometric distribution. Okay, And you can have a number of properties or results concerned with the probability generating function, and those things we will discuss in the next lecture. Thank you.